Hi, welcome back to the lecture on IoT security. This is chapter 3. Today we're going to cover IoT device layer attack surface. Okay, so we'll basically look into the IoT equipment itself. So these are some of the objectives that we're going to cover over here. We're going to explain some of the IoT hardware devices in terms of the operation wise and in terms of the hardware and software portion wise. We will look at some threat modeling, right? And we will recommend some measurement to mitigate threats and overtake. So let's take a look at a video where all these things started off. Actually, it's the history of how computing come into the place.
Of the Nazis in Europe was due in part to Germany's ability to act secretly. Throughout the war, the Germans were dependent on super-secret coding machines, including the renowned Enigma, to encrypt their messages. Codebreakers at Bletchley Park outside of London worked desperately to crack the German system. The Enigma's codes were broken with a device perfected by the brilliant mathematician Alan Turing. As the war continued, Germans designed a second, much harder to break code system used for the highest level communications. The code was generated by the Lorenz, a teleprinter cipher machine that encrypted messages before transmission. Each coded message was combined with a sequence of obscuring letters. A German operator sent a 4,000-character message twice, but he didn't follow the correct procedure to set up his Lorenz machine for the second transmission. English mathematician Bill Tutt spotted a pattern, and with this information, the Bletchley team was able to work out the complete logical structure of the Lorenz. But deciphering each message was labor-intensive, taking 4 to 6 weeks. Too long for those on the front lines. Bletchley codebreakers rushed to make improvements. Max Newman's team automated parts of the process to cut code-breaking time. Tommy Flowers replaced one of the paper tapes with electronics so that possible decryptions could be tried at a rate of 5,000 characters per second. Now, decryptions that once took weeks were completed in hours.
The first machine went into service in the early part of December 1943 and was codenamed Colossus by Bletchley Park because it was the largest machine that they'd had to operate up to then.
Suddenly, an enormous amount of information became decrypted and available, and by D-Day, it was almost an open book on the intentions of the German High Command.
To divert attention from plans to invade at Normandy, Allies launched a massive deception plan. Messages decoded by Colossus revealed the Nazis suspected nothing. The successful landing of Allied troops on D-Day was the turning point in the war. Following D-Day, Allies swiftly destroyed communication landlines. Germany was forced to rely on radio transmissions decoded by Colossus. By the end of the war, 10 Colossus machines decoded messages around the clock.
Historians now reckon that with the aid of the Mark II Colossi, he shortened the war by at least 2 years.
Allied troops returned home to heroes' welcomes. But the inventors of Colossus were forced to remain silent about their role. With Cold War tensions stirring at war's end, Winston Churchill didn't want the Soviet Union to know the Lorenz code could be broken. He ordered that the Colossus machines be destroyed, leaving pieces no bigger than a man's hand. Tommy Flowers himself burned the documentation. 30 years, the Colossus remained a closely held secret. But in the 1970s, as government documents became available, its historic and technological importance was revealed. Colossus had many features now associated with digital computers. Some regard it as the first digital computer. In 1991, Tony Sale, a British expert on World War II code breaking, gathered a team to rebuild Colossus and see it restored to its rightful place in history.
All I had initially to go on were 8 black and white photographs taken in 1945 and 10 fragments of circuit diagram kept illegally by engineers, as engineers always do.
With advice from Tommy Flowers and others, the Colossus rebuild was completed in 1996.
The Americans, for years, got away with the myth that their ENIAC computer was the first in the world, and that wasn't working till 1946.
Once again at Bletchley Park, Colossus is honored not only for the war it helped end, but for the age of computing it helped begin.
Okay, so what you just watched is actually the world's first digital computer. Thereafter, in 1945, okay, in 1945, von Neumann, basically John von Neumann, actually described how a modern computer should look like. Okay, basically based on how a Colossus was being designed. So the whole system was, how does it look like? Basically, you have an input. Okay, you have an input. You have your process. Okay, the process, and then it interacts with memory. Okay, and last but not least, it goes to have an output. Okay, so that's roughly what a von Neumann architecture actually look like. End of the day. Okay, this process actually is this whole thing is to our modern days. If you look from a CPU perspective. Okay. If you look closely, actually, if you go further, in most of the modern computing equipment itself, it should have a few component end of the day. So typically we break into this 4 portion, this 4 quadrant, right? Okay, so you have a CPU, okay, and you have a thing called BIOS. Okay, the CPU highly depend on the BIOS. The BIOS is the thing that boots up and continue from there. Of course, today we don't call them BIOS anymore. The latest name is called EFI. Okay, but it doesn't really matter. BIOS, how does BIOS work? Okay, you also have the RAM part. Okay, which is sometimes we call them the primary storage. Okay, this primary storage is basically this thing, the RAM, right? And then the process, the CPU, right? This is the CPU portion. Okay. And you have input output, but then there's a BIOS portion. Okay, and last but not least, you have a secondary storage. Okay, and this secondary storage basically is either your ROM or your hard disk. Okay, so that's typically the design of most of the modern computing. Okay. Let's go a little, let's change the color for one quick one. Okay, so why we are talking about this, because when we talk about Internet of Things, we have device, the things itself, how does it work? You need to have some form of computation end of the day. So this is how computation works end of the day, okay? Because of the Internet of Things, right? Then your BIOS basically is, if you take it in a simpler term, in terms of electronics, right? It's basically the watchdog, okay, that actually boots up Okay, sometimes you can call that boot up. Watchdog, or if you want to go even further, basically it's the clock. Okay, it is your timer. Okay, I hope you understand the timer. So basically your CPU, you need to have some form of a timer that actually synchronize with. So it start off this particular timer, and then it synchronize and it checks early days. You boot out yourself, and then it doesn't check anything. But a modern BIOS will first of all check for the CPU and check whether the CPU is operating okay. Next, you will check the RAM whether it's running okay. Last but not least, it will take from the ROM and move from the ROM or the hard disk, the actual application, okay, into the RAM itself. Okay, and then last but not least, the CPU and the RAM will interact from there and take over from that perspective, from that point on. So that's step 3. Okay, of course there's a step 2.5 here. So this is generally the design of a modern computer. No matter how small it is or how big it is, this is how modern computing actually look like end of the day. Okay, it is important for you to actually understand and know some of this design end of the day. Okay, we'll come back to this part later, the drawing. Okay, in the later part of the notes. Okay, so we shall go a little bit further, go into the further overview of IoT devices. Okay, there are sensors, right? There are many sensors in there's a hardware vulnerability. There are different kind of sensors out there, right? So what are the common possible sensor out there? Okay, they are hardware sensors, and they are all subjected to various attacks. But then we go back to what are sensors. Let's go back to a drawing, to our drawing here. Right, so what are some of the possible sensors out there? If we go back to electrical engineering, okay, electronics, electrical and electronics. Why there is a difference? Because electrical, we are talking about more about passive circuit. Okay, and electronic, we are more talking about active circuit. Okay, and there are some fundamental component in passive and active, right? Because end of the day, it's very difficult to run away. It's impossible to run away from this way of design. Whatever computation system, you still have to, the underlying technology is EE. Okay, electrical electronics, end of the day. Okay, so in terms of passive, you would have another quadrant. If you really look at it, right, your quadrant of systems, right? So first of all, you have your resistor, okay, your capacitor, your inductor, and your memory star. Okay, I know most of you may not know what the heck is memory star. It doesn't really matter. Some of you that has a EEE background, your year 1 and second year, you should know what is a resistor, a capacitor, and an inductor end of the day. Okay, so basically most of the sensor today we see is either a resistive, capacitive, or induction kind of sensor. So resistor will based on ohms, the capacitor based on farad rate, and then the inductor based on Henry. I mean that's the basic unit that people use it for, right? Because resistor, if you go back to very simple, right? Resistor, you go back to a formula, you have V equals to IR, which is your Ohm's law. Okay, so but then the rest of it, they have their own various laws that govern the capacitor and inductor end of the day. I shall not go further detail in that. Okay, but then by having that, let's take a very simple sensor, a resistive sensor, for example. Okay, what do you mean by resistive sensor? So let's say a temperature. A thermometer can be a resistive sensor. Okay, a thermometer can be a resistive sensor. How? Because I mean, all these things, if you understand your, what you call that, multimeter. Okay, today most of the multimeter are digital, right? You actually can see all the figures. So this is how all these things is being measured, right? Start from a multimeter and be able to measure out of these things. Then if you go a little bit further, we talk about thermometer. Thermometer is basically you have one piece of metal, right? Next, I'm going to change the color. Okay. Then I have another piece of metal, second piece of metal. Okay. Because of temperature change, these two pieces of metal are revert together. Okay. They will either bend towards this side, depend on the material, or bend towards the other side. One may be aluminium, one might be another one that's copper. Because of the bending, the resistance of the overall material will change. Because of changing of the resistance, you can measure to a formula, and therefore the output of this thing can be fit into a digital computer. But then of course there are conversion, because whatever you're going to get end of the day is going to be analog, right? Whatever output here will be analog. Okay, analog data. Somehow or other, all this analog data have to go back to a computer, right? A computer all the way up here, right? So how do we go do that? In between, there is another component known as ADC, analog to digital converter. Okay, so there's this component, there's electronic component that actually converts. ADC can be either 8-bit, 10-bit, okay, 12-bit, 14-bit, or so on and so forth. Okay, so let's say let's take a 8-bit one, right? The 8-bit one, how does it look like? What does a 8-bit look like, right? 8-bit means in terms of it has 255 variants, right? 8-bit means I have 80, right? 8 base 2 means 0, 2, 3, actually not this, so 255 base 2, okay, 3, then you have another formal 0, that's 8-bit, right? That's base 2, right? Correct, this is base 10, sorry, this is base 10, and then if you convert, it becomes like that, in terms of binary, right? There's an 8-bit. So I have 0, 0, 0, 0 to all the way to this, okay? And the conversion, why would I have this? This will go through a process of sampling, okay? That whatever amount of value, let's say, for example, we go back to this temperature, right? Let's say you have a particular range, let's say from 30 degrees Celsius, let's say to measure a human being, so 30 degrees Celsius all the way up to 45 degrees Celsius, okay? This will give you a range of your x and y, okay? And you can use a formula y equals to mx to figure out where exactly it is. This will in turn convert into voltage because of changing in the resistance. Okay, because of changing the resistance, this will give you a voltage. So the center point of this can be 5 volts. I mean the highest point is 5 volts, the lowest point is 0 volts, and the center point is 2.5 volts. So you just need to have this resistance to be designed in this particular way. End of the day, you can have a 0 volt and 5 volt because you can add in another resistor in between. Okay, you can have a variable resistor, in such a way that this portion will look something like that, and therefore your 0 volt will give you all the zeros, your 5 volt will give you all the ones. Okay, because of how the thing is been designed, and that you feed in by feeding these through your ADC, right? You get a binary number because of the resistance or whatever, right? Through that you can do computation because it is a digital number, which is 0 to 255, which is a representation of 0 to 5 volt end of the day. Okay, so there's a quick example of how a sensor actually works end of the day. Okay, so we look at back to the sensor portion. So we have hardware sensor, right? End of the day, let's change the in color back to red. Okay, hardware sensor are subjected to environment manipulation. So all these, it may be resistive, it may be capacitive. A lot of this thing is using temperature is a resistive one. This is inductive one because it's a thermal, it's a wind turbine, so it has magnet inside there, so it's a inductive one. Your solar panel likelihood is going to be the resistive one, right? And then you have rain sensor, capacitive. Okay, anything that deals with water is capacitive, right? Anything that is pressure or changing of the mechanical motion that actually change, right? I'm not talking about magnet, mechanical malform of this thing, whether it's a pressure sensor, temperature, or whatever, it is basically resistive. The last one, which is anything to do with magnet, is basically inductive. Of course, it is possible to have active circuit. I mean, it's possible to have things like capacity. You can use your active circuit, which is a diode, or your transistor based system. Okay, but it's not as common as a passive circuit, because at the end of the day, I would say most of the sensors are passive circuit made sensors at the end of the day. Okay, so they are subjected to environment manipulation. If any of the changes cause it, they are subject to environment manipulation. Is subject for tampering, right? Because of the changing of the material, whatever not, and then subject for damages. Okay, then we come back to diode and transistor. Your memory basically is created basically through transistors, right? Your transistor circuits end of the day. Okay, your what you call that, the flip-flop, okay, in active circuits end of the day. So memory are mostly flip-flop, so they are sensitive from, of course, the environmental hacking, or in actual fact by itself. I mean, in a very simple term, it can, I mean, people are using default username and password, which is not very recommended. This is from an application perspective lah. Okay, the actual thing is you can have a piece of hardware that actually take in and do a measurement, right? Because OWASP is not so much of a hardware people. Actually, they are real hardware people. Actually, can do at the memory level and put a piece of device and be able to read some sensitive data over here. Okay, be able to read username and password, right? If the worst is use default username and password, right? And it can even read encryption keys like that, even AES one. Okay. Next thing is a physical interface, right? What is physical interface? If you remember my drawing earlier, right? Let's go back to the drawing. Okay, we have secondary storage. Okay, this secondary storage a lot of time is to interface. I mean, your input or your output. Okay, input or output through the process. So, so physical interface, secondary storage. If it's a removable media, right, such as a SD card, subjected, someone steal it and you lose information to that. That's a vulnerability. Okay, reset to some insecure state, right? Some of these things, it may, because of some of these things can be encrypted, right? But it can be set as a read only. This is if you put this thing as a read only, but then it can be go back to write overwriting state. So there's an insecure state end of the day, because if these equipment are supposed to be read only, right? Some of the device ID and serial number that you figure out there are some vulnerability there that you can steal information from there. The serial interface connections, right? Mainly later we'll go through that serial interface, basically your SPI, your JTAG, okay, and your UART. Okay, we will go through all these things slightly later, okay? And then user administrative access and previous escalation, because some of these physical device may have some of these issues. Mainly a lot of time is this serial connections, okay, the key part, the insecure state and the removable media portion. We will cover that in detail later. Okay, next thing, the software itself, okay, the firmware, the software. This is a piece of software that goes into here, okay, or the ROM itself, the memory, right? This is ROM, okay. So go back to the diagram, right? The thing I keep on mentioning here, the storage, this thing. Okay, the ROM, okay, the firmware, which is loaded into the RAM itself. Okay, it may hold the encryption key. This is RAM, this is RAM. This encryption key is inside the RAM. This is inside the hard disk or the ROM. Okay, so it appeared twice, but then it means different things. They are stored at a different media altogether, right? Hard disk, of course, is a magnetic media. I mean, the ROM can be a solid state device, same as a RAM, but then they are different because this keep state after even during reboot. Okay, and some of the thing can be a hard code credential, which is quite bad. Normally we don't try not to do that anymore, to have a hard coded credential, the username password. Okay, there may be some background account, the version updated, and some of the security feature of API exposed at the ROM itself. So there are some of these vulnerability for the attack surfaces for firmware, device firmware. Okay, this is just the firmware itself. Then the update mechanism is the communication from the firmware and do the update. Some update is done without encryption. Some update is not signed, it's not digitally signed. Okay, so we don't know whether is it really from the manufacturer or not from the manufacturer, right? The location, okay, update location, whether is it writable or not writable. Okay, call back to the device itself, right? So if you put a read only, then it's not writable. So how do you design this particular stuff? Okay, of course it may not be just this. If you talk about ROM portion, there is some of the thing. There's a thing called, to do this kind of protection, there's a thing called eFuse. Okay, it's not only for cyber security, but then for the sake of IP rights, the intellectual property things, may people not be able to copy out the firmware. Okay, the update verification and authentication for the firmware itself. Is there a malicious update? End of the day, is there a missing update mechanism? Actually, go further than that. It has to do with the processor, different kind of processor, the communication type. Mainly this portion of the firmware is done at the IETF. Actually have a standard to do this. Okay, this is known as there's a working group that actually in IETF actually doing this. Okay, the firmware itself is tip for IETF. Okay, and the firmware update is software firmware update, so it's called SWIM. Okay, it's a firmware update inside the IETF standard itself. Okay, we shall go through some of these things in the later slides. Okay, so we go into the constraint devices overall, right? We covered just the overall general what are the weaknesses. Let's go into the constraint devices. So what are constraint devices? A lot of IoT device, okay, O1 are designed using a very highly limited power for many years. I mean, somewhere from the early days, where it's connected to internet. Okay, the key thing is internet, right? So internet, we're talking about what? We are talking about as old as the 1980s. Okay, somewhere you are connected to the public network end of the day, right? It may be PBX or whatever. The telephone network is really considered so-called the internet. That okay, later we'll go through some of this technology that go as far as connected to the telephone network. Okay, telephony network. Okay, which is yeah. Okay, so that is the part. So those days when it's early device, when it's created, it is most of the chip is 8-bit processor. Okay, because it need to be low powered, low in memory, and low in processing. Okay, so for a very long period of time, even that this is the early days processor are pretty big. Okay, all these things are the communication are very limited, and the chance of encryption is not so possible when you're doing 8-bit, right? It is very hard to do it at 8-bit processor. So some of these constraint devices, what are some of these constraint devices? There are several classes. All these things are classified under ITF. So there's a class 0, class 1, class 2 devices, which is in terms of the RAM and the code size. These are some of the code size. Okay, so one of the issue of some of this constraint device is a lot of time the RAM size are pretty small, right? But if the code is much bigger, and then the code, if it unfortunately if it's overwriting into the memory space, it may crash the whole entire system. So therefore, if it's a single application, let's say you have a RAM, this is a RAM, typically in a CPU architecture, right? Your RAM is typically a stack. Okay, we call them a stack, and the lowest level, let's say it's 8-bit, so it's all the way from 8 bits, right, all the way to 1111, and then 1111, right? So this is the memory stack. If you load the memory up to a certain point, just like this is a water tank. Take example, it's a water tank. You put in the water, okay, it's fine, it can be stored, right? But then if there are too much of the application, it may overflow. Overflow becomes an issue. Okay, overflow becomes an issue. So let's say you have whatever, if you have a hot liquid that goes inside and then overflow, then it may cause harm for the whole entire thing. That whole entire thing may melt down. Same for electrical system. If you overflow it, it will cause harm to the system end of the day. Okay, whether it's a digital system end of the day. Okay, so it will not work anymore. It will not work properly anymore. So we in the IT term, we don't call them overflow. We call them buffer. We call them buffer overflow. Okay, we also call overflow, but just the name. If you don't call it RAM, we call them buffer because it's a temporary storage. RAM is a temporary storage. Okay, so buffer here means RAM. Okay, buffer overflow. Okay, then some of the device today is there are smart sensors that has a CPU that connect to some sensor, so they are called smart sensor. Okay, there are some more powerful devices than smart sensor. Those are called embedded equipment, right? They have a lot more powerful CPU, right? They have not as constrained as these, right? The CPU is a lot more powerful. And then last but not least, there are some another set which is a prototyping. One is called Raspberry Pi, one is called Arduino. Okay, both are embedded equipment. Okay, and they are used for prototyping to design some of these things. More and more industry are using them for real production usage. Okay, in the real workplace. Okay, because of the chipset shortage, right? Arduino is actually came from a real chipset, so they are the ATR. Okay, chipset by Micro. Okay, and Raspberry Pi is by the Raspberry Pi Foundation annually. Okay. So there is overview of high level in terms of the processing and the memory portion. There are different kind of CPU type out there. Okay, today when you talk about IoT, in actual fact, pre-IoT, there are different kind of processor type. Okay, the very well-known one that you use in your everyday life is x86. Why you call it x86? Because Intel is the company that designed this x86 CPU. Okay, so in early days, I mean, beside the very first one, which is known as a 4004 processor, which is meant for a Japanese company for calculator, they start building a computer for PC, which is based on this ending with x86 numbering. So they have a 8086, okay, which they call them an XT machine. They have a 8286, which they call them a AT machine, and then they follow by a 8386. Okay, and these in terms of the CPU itself does not comes with what you call that is until here. Okay, it is basically the memory itself, the RAM itself are not highly protected because viruses and malwares are not very common then. Okay, but they started to have do a better job over for memory management when it hit 386. That's step number one for cybersecurity. Step number two, over here there is the thing called 8386, 387 that has an additional functionality known as a floating point unit. Okay, this floating point unit allows you to accelerate in terms of computation for a decimal point. Okay, what do we mean by that? Very simple. If you just do an addition or subtraction, you don't need to have a floating point system, right? It's 1 plus 1 equals to 2. Right, you don't need to care about that. Even for multiplication, 2 times 2 equals to 4. There is nothing on floating point. But then if you do a division, right, 1 divided by 2 is equal to 0.5. That is where your decimal point is. So that is where how for floating point system you need to accelerate. This is where the 387 comes in. The last one after that is 486. 486 is the last of Intel that use 86 naming convention. Okay, but even today we are still using, we call them the x86 because of this all this series from 86 to 486 machines. Okay, for Intel. Thereafter they don't call Intel, they don't call 86 system, they call Pentium. Okay, because of marketing and because of other companies start coming in, because 386 AMD. Okay, let me have some change of color. Okay, they have support, Intel has support to AMD to start building CPU for them, starting 386. But then because of AMD and there's another company called Cyrix that's come into the picture, so they decided to call the name not 586 but then Pentium. On the other hand, AMD still built a machine called 586. It's just the next generation of whatever 486 is. Okay, 486. So that's the story of the x86 machine, the PC, basically your PC, your notebook, okay, or even some of the embedded systems. Then there is another two other kind of technology CPU that comes in at the same time. So one of them is called ARM. So what's ARM? Let me erase some of these things so that it's better for producing this thing. Okay, let's look at ARM. Okay, ARM started off by the British, so it's for the BBC, It's not your British broadcasting computer. It's a British built computer. Okay, British built computer end of the day. So it started off from a company called Acorn. Okay, and Acorn built Acorn RISC machine. So then we come out this name called RISC, right? Your x86, the last from 8086 to 8046, which just now we mentioned, are basically complex instruction set. So then now we are going into this thing called reduced instruction set and complex instruction set. So what are the difference, right? So let's say you have an instruction for a computer to process. I want to add two numbers together. I want to add this number plus a second number and get you the final answer, right? This is the system. So if you want to add 10 numbers together, so by complex instruction set, you can have there's maybe a thing called add 10, right? Add 10, which is not necessarily 8-bit long. It may be 16-bit long, and you can add this 10 number together. So you make use of a thing called complex instruction set to do it. Whereas if you have a reduced instruction set, which is a way to talk the computer process, they don't have this thing. So they have to add it 10 times. They just have a simple instruction such as add only. So they have to do 10 add altogether. The beauty of this reduced instruction set is within the clock. Remember we mentioned about clock earlier on, right? For the BIOS level, right? You have a clock, right? This is clock, okay? So if we think in terms of the clockwise reduced instruction set, within one clock cycle, you can have many instruction. Okay, whereas a complex instruction set, one clock cycle can only have one instruction. Okay, so in early days, it's easy to build a complex instruction set. So most people build Intel move to build complex instruction set, and they are quite famous for that. And the most of the computer are running pretty fast then. Okay, it have reached to a point of Pentium that the thing has changed. Pentium came in somewhere. This is 80s, early 80s to 1980s to early 1990s for the 10 years or so. Okay, starting from 91, 92, we shift over to Pentium. Pentium natively internally, okay, it is a RISC machine. Okay, it wants to go more than one clock cycle, more instruction in one clock cycle. So they be able to do these things. So there is just a differentiating portion from 486, and they no longer call it 486, and then it moves to Pentium. And Pentium, the other key differences is Pentium reached a certain point. It's still 32-bit natively, but internally it start running 64-bit. Okay, it's a starting point of 64-bit, but they are not very successful in moving to 64-bit. Okay. So that's the part on the well, I'm not going into ARM itself, right? ARM, I mentioned a little bit about RISC. Okay, then we talk a little bit more about the ARM portion. Let's clear all the thing. Okay, when we talk about ARM is split into talk about modern. ARM is known as Advanced RISC Machine. Okay, Advanced RISC Machine, which is here, Advanced RISC Machine. Okay, it basically split into the A series, R series, M series. Okay, and some of the well-known M series is used inside your mobile phone, your SIM card. So you do own a ARM processor, and this is mainly inside your mobile phone. Okay, so that's the key portion I want to talk about ARM. Okay, so we cover what is a RISC, what's an ARM, and then between this is the R series is in automotive, which is car. Okay, car. Okay, so this is part on the ARM portion. Okay, next we need to go a little bit further than that. I need to clear all the ink. Okay, next there is another processor known as MIPS, right? MIPS stands for multiprocessor without interlocking pipeline stages. Okay, first of all we have the Intel. This is starting from the 70s to somewhere around the starting for this until today. Okay, ARM actually came when we need to have the mobile phone, which is the late 90s. Okay, we call them the late 90s. Okay, so in between here and here, somewhere in the mid of 80s. Okay, mid of 80s, then we started have MIPS. Basically, the famous one is Sun Microsystem. Okay, they built their own processor which is based on MIPS systems. Okay, where do you see MIPS today? They are mainly in Sun Microsystem. Sun stand for Stanford. Okay, University Network. Okay, so you can see this word network. The keyword why I want to mention Sun, because of network, right? So MIPS is a processor that is designed highly for network. So at home, where you have a network, the easiest thing to look from your home is your home router. Okay, the main company that built this chip manufacturer, okay, they ask a third party to manufacture for them, but then end of the day it's put under their name is Qualcomm. Okay, Qualcomm. Of course, Qualcomm also have ARM processor. Things inside your phone is also from Qualcomm. Things inside your router, which is MIPS, is also from your which is at home, right? Also from Qualcomm. Okay, so Qualcomm are one of the big manufacturer. In actual fact, builds a lot of IoT. This is a main chip manufacturer from a lot of IoT equipment. Okay, of course there are a lot of other companies, right? That I'm not mentioning here, but then a lot of them actually, some of them that makes use of ARM based. It can be the old Philips. Today is known as NXP. Philips. This is Philips. The old Philips, and then they become MXP. You have Texas Instruments that build ARM. Okay. You have ST Microelectronics that build ARM. Okay, so all these companies build ARM processor. MIPS is mainly Qualcomm. Okay, because of their nature, the network company. Okay, and then of course devices you have beside Qualcomm, which is your phone. Then all these are the main one that actually built for some of other things, because they build not only the A series, M series, and R series. Okay, because the car they get equipment for all these things. Of course, all these are from the West. In Japan, they also built some of this ARM processor. Okay, but they are not so famous end of the day. So, we have mentioned about CIS processor, right? Then, if you remember just now, I mentioned about what you call that. I erased that portion. It's okay. So somewhere in between the processor, we have in the midst of the early days of processor, we have 387 just now, right? You have floating point unit. Those are the accelerator beyond a basic CPU. A CPU typically, if you look at it, there's an arithmetic logic unit, okay, that actually do all your plus, minus, multiplication. It's just a calculator. It's the same. It's exactly the same as a calculator. A computer is nothing. It's just more advanced calculator only. That's all. Okay. And the division, of course, very slow here. But then, if you have a floating point unit, you will increase the speed. Okay. But then, as time goes by, we need to do more things. We want to do a lot more complicated stuff. So the CPU start to have embed more complicated system into the CPU itself. So what are some of the more complicated things that they add into the CPU itself? Because end of the day, we not just want to add a simple number, okay, to another simple number. We want to add many numbers, such as a matrix, and then to another matrix. Okay, so this is typically known as so just add two number or many numbers. You move from a scalar processor to a vector processor. Okay, this is 1D, this is 2D, this is 2D, right? This is 2 dimensions. So a vector processor. Okay, so a GPU, it is a 2D processor. It allows matrix. Basically, you have 1 0 0 1 plus 0 1 1 0. Where all these things is being used, your compression and uncompression of your picture format, such as JPEG, okay, or even movie MPEG. Okay, this allow all these things to happen very quickly. So it moves into vector processor. So the GPU is one of the things that allows your vector computation to become a lot faster. And then you need to go many frames per second, right? You want to go at least 30 frames per second so that you actually can watch a proper movie end of the day. That's where your early days GPU is about. Okay, to be able to do all these things. Of course, all these things is possible to do handle encryption and decryption tasks. That's a secondary usage end of the day. But then there is a part mainly why there is a GPU involved inside your today's modern, even for your what you call it, your mobile phone, because end of the day you also want to take picture, right? Take photo, right? Take photo or take video, whatever, right? So at the camera level, not just the display, it also involved inside there. So that's where the main use of the GPU. Okay. Last but not least, there's a thing called big little computing. Okay, they're using different core. There's a thing called the power core, and then the efficient core. Okay, because not everything require very powerful CPU, right? Because end of the day, you want to extend the battery life of your equipment, so you may use some of the efficient core. The early days of Raspberry Pi are using some of the efficient core, like example A53 efficient core. That is for Raspberry Pi 3, okay, version 3. And then the newer one, version 4, is using a power core, which is a A72. Okay, so that's the difference. Okay, of course they can have a big and little. Some of the mobile devices, your phone, especially your phone, can be a mixture of A72 and A53. We are talking about very early days equipment. Of course, there are newer versions, okay, such as A55 and A57. We are talking about version 8 of ARM. Okay, here A72 can have A73, 73, okay, A76, A78. Okay, some of all these are the famous one. There is iteration. Okay, the upcoming Raspberry Pi is A76 version. Okay, in terms of the processor itself. So next thing is about memory. We talk about quite a lot about CPU, so we move into the memory. Here memory basically is some of them are the RAM itself. So we go to the RAM first. This is RAM, the SRAM and DRAM, right, which is holding the operation code. Okay, so if the thing is been powered down, the information is lost, right? Then there are secondary storage such as SD card, okay, and non-volatile memory, EEPROM, okay, and erasable ROM. Okay, so there's there's EEPROM is a very common one, which actually store most of the firmware, bootloader, and some of the critical information. Okay, as I mentioned, BIOS would load whatever from the, whether it is from an SD card, which is how your Raspberry Pi works, or from your EEPROM, which is how your Arduino works, to RAM. End of the day, whether it's a static RAM, normally most of the time it's not static RAM, because static RAM is expensive. Most of the time it's just DRAM. Okay, and be able to process from that point. Okay, I mean, static RAM will only apply for expensive equipment such as routers and so on and so forth. Okay, and switches. IoT also have many physical port. End of the day, right? The basic one that you see, the simplest one is your phone, okay, and your notebook. They have USB and Ethernet. Of course, today we talk about high-speed Ethernet, Wi-Fi, and so on and so forth. But then some of these things are the standard equipment that comes with even for IoT equipment. Okay, these are standard ports. The most common one, the most basic one that actually go as far back as the 1980s is your UART. Okay, 1980s. That's why I say IoT equipment goes as far as back as all the embedded system, which is leading the 1980s, where we start to have a CPU and all these things with a motherboard and so on and so forth. So the UART basically are three cable. One is to transmit, one is to receive, and a ground. Okay, and it is possible for attacker to capture the data for this because everything is in plain text. The key thing is until today we are using it because we use the UART. There's my mouse. Okay, we use UART. Okay, a lot of time for updating firmware. Okay, so your EEPROM, just now we talked about the memory, your EEPROM. Okay, when we want to load the program, or your SD card, a lot of time can be go through the UART to load the program. In actual fact, you can see all the command lines. You can log in with a username and password, but then they are all in plain text. The more secured one that most people are using today, which is have an encryption for the username and password, is known as JTAG, which is this thing, right? Joint Test Group. Okay, it is a protocol. It is not a communication protocol, but a common protocol for testing and debugging. But then a lot of time, it allows to look into the controller, and then there is the key one. In most of the time, the key one that actually put it into the firmware. And in actual fact, a lot of time we normally don't use the JTAG for the portion because it's a lot more secure than UART. So normally we go into JTAG, but then the JTAG doesn't have most of the time when they finish the design of the printed circuit board, I mean something like that, the JTAG connector is normally removed, right? Doesn't have a JTAG connector there. Okay, but it's possible to do a shielding on top of that. Okay, so for attacker to do that is a lot more complicated than serial connections. Okay, then next thing, there are two other physical port. One is known as I2C, one is known for SPI. Okay, let's talk about SPI first. SPI, if you remember earlier on, we go through at the beginning. Okay, we talk about input and output. Most of your serial connections, right, that talk about your storage, whatever, most of them are SPI. Even the RAM can be SPI. Okay, even for the RAM can be SPI connections. Okay, but most of the time, all these connections can be SPI. Okay, which is a serial connections. Okay, it depends on the speed wise, right? But then most of the time it is meant for either the sensor, okay, or actuator, whatever is input or whatever is output. Okay, so that's what serial peripheral interface is actually 4. Okay, yes, so 4 serial connections. Okay, the key thing is you have a clock. So if you can run a faster clock, you probably can use it for memory, but then most of the time it's not used for that. It is either meant for sensor or actuator, because it can cover a longer distance. Okay, it can go for a few feet away. Okay, the shorter one, then it comes to the other one, okay, which is I2C. I2C is for chip to chip, right? Often it's a much shorter distance, few cm, okay, between chips on the same port. Okay, so it's between the microcontroller to the RAM and the EEPROM, okay, for the program itself. Okay, so that's what the I2C is mainly for. Okay, that is the main physical port that most of equipment comes with. Okay, such as Raspberry Pi, Arduino, or whatever embedded system that comes with some of these ports. Okay, they may not be having all the ports, but then they comes with some of these ports that allows you to do with. Most of them, as I mentioned, definitely come with UART. Okay, they definitely will come with UART. Whether they come with I2C or SPI, that's the other part of it. Most of them will definitely will have JTAG, because end of the day, somehow or other you need to test the board, so they are using JTAG for testing the board itself. Okay, so these are the common physical port for any device. Okay, then next thing is we come back going through some of these things, so we talk about more powerful computation, right? What is an embedded system? Basically, compared to a constrained device, it has a lot more powerful computer inside there. Okay, in terms of CPU, in terms of the RAM wise, in terms of whatever wise. Okay, some of them may be a sensor. Okay, that may include smoke, motion, gas, and so on and so forth. Sensor inside there. A lot of time we don't call them I don't call them the sensor. In actual fact, it's wrong to call them the sensor, because they have a lot more powerful circuit. It's not just microcontroller. It has a lot more circuits plus microcontroller, which is a lot more powerful RAM or whatever, or more powerful one. Most of these things we call them instrument. Okay, the actual correct name for that is actually known as instruments for things for your input. Okay, and then for the rest is your control, your actuator. A lot of time, the key part of the actuator, which is what you're going to control. I mean, there's a few things that you can control. It comes back to your basic EE portion of it, right? Your resistive, your capacitive, and your inductive. So most of them are inductive, basically your motors. Okay, one are the very common one, because they make use of magnet for driving all kinds of things. If you think about it, just like a human being, one of the things that you will be able to control your hand, your leg, and your head or whatever, it is a motor action. Okay, it's just vertical motion or physical or horizontal motion and everything. So motors can run most of the stuff. Of course, in electronic system, that is possible to have a few more different things based on active circuit. So you may have LED, you may have something that burns resistive. So end of the day, it's possible to have light. Of course, light is a good indicator whether the things is running or not running. Okay, so actuator can be also light. Okay, for indicative, can be have most of the time are motors and the inductive magnetic equipment. Then there's another last piece that is sound, okay, which is actually motor-based systems. Okay, there's very little actuator that is capacitive. There's not a lot of them that is capacitive. Okay, sound is basically motor. I mean the magnetic portion, but sound is a slightly different thing. Even though it's a you know, typical speaker look something like this, and you have a membrane here, and then you have a piece of magnet here. This is a magnet. Okay, and it produces sound. So if I start spinning this thing, it produces sound. Sound is important because a lot of places for alert, because sometimes you need to know the alert. Want to know because the visual one you may not see it because light require a direct line of sight. It require a direct line of sight. Okay, you may not be able to see it, right? Your eyes don't see it. Your sound is omnidirectional. So for any emergency or whatever, it can be serve as an alert. So sound is also a very important portion of the overall design when you come to some of this equipment and everything. Okay, so a lot of this embedded system make use of a microprocessor, a microcontroller, and then a microprocessor is basically a microcontroller has just on whatever the physical port plus your microprocessor inside there. Okay, so it does both. It has a lot more connections and things. So a microcontroller is a self-contained. It include flash, RAM, serial port, and some other peripherals in a single chip itself. Whereas a microprocessor is just a microprocessor, it's just a CPU. That's it. It may not have all the serial or whatever connections that comes with it within the chip itself. Okay, so some of these system can be directly programmed or indirectly programmed using a CPU. Okay, some of them are basically a stripped down Linux. Some of them may not. A lot of them are real-time operating system. Okay, the key thing is called real-time operating system. Some are just one application, right? If you talk about very simple one, well, go back to constraint device, they're just one application. But you go to embedded system, a lot of them are actually real-time operating system that is not necessarily Linux. Okay, what are some of them? Real-time operating system, QNX, VxWorks, okay, are some of the common real-time operating system. Okay, debugging of the program of this embedded system is handled differently compared to PC software. So PC may develop in the same computer and run on. So on an embedded system, typically you find a PC and at the end of the day you write whatever code that you need and then you push it, including the whole, it may include the whole entire operating system into the device itself. So that's what an embedded system is at the end of the day. Okay, it applies both for the constraint device, basically how you program a microcontroller. Okay, it's basically microcontroller end of the day. So how you program a microcontroller, you typically build outside the environment and then push everything into the system itself. Okay, so that's typically how embedded system works. But of course, if you start looking into things like Raspberry Pi and somewhere around that kind of equipment, then you can directly program it within the system itself. There are more and more embedded systems that allows you to program within that system itself. Okay, it is possible. Okay, so it is highly possible to do that as well. Okay, so then it brings us back to programming really, because we are discussing programming, right? So programming, there are two main kinds of programming. One is known as compiled code, right? One is known as interpreted code. Compiled code, when you talk about programming in IT world, so what we talk about in terms of programming. So end of the day, what you're going to get, right? This is your CPU. Your CPU can only understand a thing called machine code. Okay, it only understand ones and zero. Okay, it doesn't understand all the programming language that you do. So there are two main ways of doing this. In order to get machine code, typically you have to go through a thing called assembly language. Okay, but assembly language is too difficult to understand a lot of time for most people, right? And of course, machine code is the worst. Okay, sometimes we don't call them machine code; we call them the binary code. Okay. So for assembly, you can assemble to machine code. But then in order to make human programming a lot more efficient, so we have invented a thing called a compiler. Okay? And it's readable in terms of a text editor and then later compiled, okay, into an assembly before it goes into a machine code. That's what actually this thing is talking about, right? So some of the common language is C and C++, okay, for a long period of time. Okay, of course, there are some other language that is also available. By the way, there's also a thing called Java. Java is very common in embedded system also, right? Same as C and C++. Java, there is a mobile edition, ME, call them mobile edition, which is very common in your SIM card. Okay, the SIM card is a communication device, so it's definitely Internet of Things. Okay, your mobile phone, eventually end of the day, your SIM card is one of the key things. If you want to look a little bit further beside your SIM card, a thing that comes with a chip that look like a SIM card is the chip inside your credit card. Okay, so it's the same thing, right? So but then it does less communication compared to your SIM card, right? So, but then all of them are running on Java ME. Okay, so Java is a very common language that's used for doing this kind of processing. As I mentioned, most of the time you're using ARM-based M series processor to do this. Okay. Then, if you talk about modern compact programming, Rust is one of them, slightly more modern one. Okay, that's about all that I want to cover. Visual Basic, there are some, but they are really industry-based systems for Windows. If you talk about Windows-based system, then Visual Basic. Windows-based, if you talk about Microsoft Windows-based systems, okay, then Visual Basic comes through. Okay. So, but then there's not a lot of embedded that doesn't have a GUI or whatever, because if you want your Microsoft Windows one, basically means that you have GUI and what's not. Okay, so depends on how you see it, right? This thing must comes with GUI, graphic user interface. Okay, so the majority of the things does not come with a GUI. They are just equipment and small little chip that appear in thousands or millions of places. Okay, next, interpreted code. Okay, there can be a few the other programming that most of the time talk about interpreted code, such as if you have equipment that require for you to do some configuration, but then you have no interface, you may do a QR code. They may give you a QR code. Okay, and at the end of the day, provide the interface for you to program. In early days, of course, then some of the QR code, if it's it can be using Adobe Flash for the connectivity to create that QR code, or it can be Java. Okay, but all these are compiled code. Flash and Adobe Flash and Java are compiled code. Okay, so but internally, it is possible. Let me just erase this part only. Let's say it is a web page, and you want to call some of this Java and Flash, right? You want to call this Java or Flash. So in order for that to take place, in early days, of course, it is hard coded through CGI. If you understand what is HTML programming, right? In early days, we are calling CGI or PHP or whatsoever. Okay, then or Perl. CGI is nothing but Perl, right? But then later, part of the web page one for you, the configuration is the JavaScript. So this is where all these things in the early days, when you have a GUI for you to call your programming in terms of your embedded system, that comes with a GUI. You want to have to do some form of configuration. But the actual firmware itself, it can be a thing called MicroPython. Okay, interpreter. Or the other one, which is not written here, the main one is Lua, Lua. Okay, which is very common, which is an interpreted language. So in terms of interpreted language, there's all some of these things. Okay, it's not really Python, it's MicroPython, and then the other one is Lua, Lua. Okay, so these are some of the programming language. So what does interpreter. Basic was an interpreter language. Okay, interpreter language translate instruction to a form of machine code that is run at live. So it's line by line. So it's at that line, it runs that line, it runs that line, it runs. Your Perl and your PHP is not really an interpreter. It is more compiled. So it's more back to C and whatever. Your JavaScript is an interpreter. Your MicroPython is an interpreter. Your Lua is an interpreter. Okay, so when you come to HTML and you talk about Perl and PHP, which is your CGI and PHP, right, at the back end, they are actually not really interpreted language. They are more compiled. Okay, so there is a differentiation. Do forgive about this thing. I think the person who write this thing actually don't really understand how actually programming in detail programming works. Okay, so that's some part of the thing that you need to take note on. Next, when it comes to this part, some of the system may be Linux based. Okay, Linux based will have shell. So a typical shell language that if you have using a Linux such as Raspberry Pi, then at the back end the shell language is called Born Again Shell. Of course, there are many different shell language beside Born Again Shell go to shell, because shell language come from Unix systems such as K shell, which is in some microsystem, C shell, right? This is more like C language, K shell, bash shell, so on and so forth. Okay, for be able to perform some repetitive tasks within the language itself. So all these programming language, some of them has weaknesses. Example, that's which we are going to cover, right? Interpreted language is can be easily modified by attacker because it stored them in text form. Okay, same for some of these shell languages. Okay, they are different. Programming language is one thing. Okay, Python, you can put it as like a script. It's just a more complicated, more comprehensive script. Okay, bash shell and then some of this C shell, whatever, is a less comprehensive script, but they have different functionality and already. So sometimes it's easier to program using bash, sometimes it's easier to program using Python. Okay, next, there's another for Microsoft. There are a thing called PowerShell, but then there are not a lot of IoT equipment that's run on Windows unless you're talking about industry equipment, right? There's embedded Windows or so on and so forth. Okay, most of the people today are shifting towards a lot more on Linux rather than Microsoft. There is still Microsoft system out there, right? If you talk about bank system, your ATM, right? Your bank ATM. Okay, so those are your Windows systems. Okay, when you're flying onto a plane, they have interactive systems, or on the vehicle itself they have an interactive system. Some of them are Windows. Okay, so if you Microsoft system, most of the time are interactive IoT systems. They have a GUI. Okay, so these are some of the way to differentiate between some of these systems. A lot of them that doesn't cover GUI or whatever is either Linux or real-time operating system. Okay, RTOS. We come back to RTOS. Okay. Then on the other side is we have just covered interpreted code, right, and scripts. The other one is compiled code. Compiled code, you need to do the way that hacker hack it is through debugging during the debugging stage. So if some of the device are in, because a lot of time is either in processing mode or debugging mode. So some developer may have forgot to turn off the debugging mode and keep the debugging mode alive, then it's subject for that IoT device for hacking, right? But then it is possible to turn off the debugging mode and switch back to just pure operational mode, then the risk of that is lower. The key part of this debugging mode, remember there are two physical ports. One is JTAG, which is mainly for their purposes. Second thing is your UART. Okay, sometimes your UART doesn't appear as a UART, it appears as a USB. Okay, one of the lab that you have done serial to USB basically is that. Okay, so next let's move on to the next part. So then we move on to the debug mode. Since we are talking about the debug mode, right? So there's a debug mode or boot mode. Okay, they are slightly different. Debug mode allows to talk about your program, how your program actually works. Boot mode is talk about at the BIOS level, how does it boot out. Okay, because if you remember just now what I mentioned, there are two entire layers in terms of your system, right? One is your CPU talking to your RAM, your memory. Okay, and your program is running here in your RAM already. Okay, that one is basically your debug mode. Okay, when you talk about your RAM, your read access memory. Okay, your program is running. Okay, and then there's a debug mode there for the developer to do it. As I mentioned, a lot of this system allows you to go into some of this system that allows you to look at. Okay, your boot mode is slightly different. Boot mode talk about yours at the BIOS level. Okay, then you're loading the program to the RAM itself. Okay, do you allow this BIOS to do some changes? That's where the boot mode comes in. Okay, because sometimes in order for you to do debugging, you may require to go into this BIOS and allow this thing to happen, and therefore they lump debug mode and boot mode together as one, and sometimes you can access through some keystroke. Okay, that is sometimes, but most of the system is not like that. Okay, during the booting out, there is a thing that you need to specify. Okay, to the BIOS, you say, I want to go into the debug mode end of the day. Okay, sometimes you need to go further than that. So if let's say you have a mobile phone system, you have to go way beyond that, and then you need to do quite a bit of changes before you can go into the bootloader site and actually do all the necessary changes. Okay, and some of the authentication could be bypassed when you're running on debug and boot mode. Okay, the way to do this is not so simple, right? The key portion is to come back to the physical things that they put certain things on top of the processor and they start scanning. Okay, if that is the way to do it, even you have authentication issues, because it's not just authentication, the cipher is also being cracked. Okay, such as AES. But this is not easily run by any person out on the street itself, so it's not so simple. Okay, next, beside the booting process, which is mainly the BIOS and then the CPU itself, then you move into the firmware itself, the operating system when you're running it, right? Part of the operating system come with some trimmed down use of the operating system. Okay, they can be open source, they can be commercial, right? The more of the open source version is known as a BusyBox, which make use of Linux, right? So there are quite a bit of the router switches and some of this system. The key part that comes from here is what we call them the Open WRT. Okay, system actually make use of BusyBox as the key software inside there. Okay, and then it's possible to boot out the thing if you understand how the CPU and the RAM works. There are some other things such as Android embedded, which is a lightweight Linux version for some of the mobile devices. Okay, that can be used for some of these systems. So there's a Android, right? Your Android phone. Then there are some other commercial system, as I mentioned. VxWorks is a real-time operating system. Okay, just now I mentioned the other one is QNX. Okay, and this is not really an operating system. This ARM, Mbed, and Arduino are just a library. Okay, so they are not a full-fledged operating system like VxWorks, QNX, or Windows IoT. Okay, there are some libraries inside there that is loaded together so that you actually can run your program. And a lot of time when you talk about ARM embedded and Arduino, you're not loading a full operating system. So the key word is, what is the difference between an operating system and a non-operating system? So there is a separation here, okay, to be very clear. OS will have to deal with things like memory. They do memory management. Embedded system, okay, such as ARM Embed and Arduino, doesn't directly deal with memory system. Okay, the programmer have to write that portion partially, not entirely. Today, if you talk about modern one, some of the things that Arduino will take care, some of the things that Embed will take care at the library level. Just call the library, it will at the back end take care for you. But in actual fact, it is perceived in that way that it is not a full operating system. It's not like a real-time operating system. Okay. The second thing is it also deals with network. Okay, or your operating system deal with a lot of your peripherals, especially your network portion. Okay, embedded and your ARM series, you have to code the whole entire thing from scratch. It doesn't deal with this thing automatically for you. So that is the key differences between operating system and a non-operating system. Okay, just load libraries of this thing. Of course, here we'll have a better memory management because you can run multiple processors at the same time, such as threading. Okay, because it has a proper memory management unit for all these kind of systems, because it doesn't come with a memory management unit, the hardware, right? So you only have limited thing. You will only run one or two programs. Most of the time, one program at every instance. So a single process. It has no threading and all that. Okay, so that's the key differences between operating system and non-operating system base. So most of the constraint device are, well, this. Okay, this one, I'll draw it properly. Arduino. Okay, Arduino system. Okay, next. So what are some of the vulnerability and attack at the hardware layer? Okay, so for physical equipment, physical vulnerability for constrained device, for very low end device, right? They may be placed at remote location, right? It may be difficult to implement. So some of this equipment, well, it's not just constraint whether if embedded system, because it just put constraint, but actually applies to some of these IoT equipment. The theft of the equipment, stolen, right? Physical damage of this device, disable the device by removing the power, disable the communication, disrupt the communication, disconnect the cable. Okay, it may be a cable, sometimes it just maybe just wireless. Okay, if you talk about some of the very system that is very low end and it depends on the power itself to do it, you may have a jammer that be able to jam out the signal. For example, you talk about RFID system. Okay, it's just an ID system. So it's also an IoT equipment, right? It's very, very low end CPU end of the day, right? Very, very constrained device. So it's possible to do it. There are some sensors that's very, very low end, something like RFID, but then they are put inside, let's say, buried inside the bridge, buried inside the road. They are also sensor like that, or buried inside the building itself. Okay, so some of this vulnerability that there may be some jamming device that jam out the signal end of the day. So that's what we mean by disruption. Okay, so is it possible some of the things you say, oh, you put some of the video surveillance when possible, but when possible, okay, it is actually not possible to do for all, because there are a lot more of all these IoT equipment way beyond what a camera can do. Okay, only higher end devices such as embedded systems that it's possible to put a few, but it's not be able to do a full coverage. Okay, the next thing is to provide a tamper-proof and a tamper-resistant type system. So tamper-proof, sometimes in US there's some standards for that. Those are known as FIPS standard 10140 in terms of all these things. This includes some of the crypto that need to be fit into some of these embedded systems. Okay, some of the encryption method that comes into some of these things to ensure that that is tamper proof, and in terms of the hardware wise, the casing wise, and all this kind of stuff. Okay, so then the other one is a tamper resistance type of housing. So some of this casing that look something like that not easily removable, and some of this equipment need to be put not easily reachable end of the day by people. Right? You need to climb a tall ladder or whatever that not easily accessible, and it may have some housing or casing that actually locked up, okay, to prevent normal people to access it. So it means at the end of the day, people would need to understand in terms of civil engineering where and how to properly put in some of this equipment. Okay, there are things such as false ceiling that allows you to put in quite a lot of this equipment inside there. So people will not be able to see it, so they won't be able to destroy it. Okay, so there's a thing called false ceiling. Okay, so some of this equipment can be put inside a false ceiling. The next thing is physical device security. Some of the equipment can be moved. Okay, that can cause loss of calibration. In actual fact, some of the sensor normally must always do a recalibration every now and then. So it is important that they can be removed and then used for calibration. Okay, but then some of these sensors can be able to trigger alarm. So that's where the sound is, right? If they are not properly adjusted. Okay, and some of these may have storage, such as SD card, could be stolen, could be destroyed by the attacker, right? Can be removed, right? Some of the standard surveillance and security protocol should be there for first layer of defense, right? And some of the physical device should include ensuring what you have access to the device. Make sure that you have some battery backup to some of this equipment, okay, to make sure that it runs constantly, so that someone trying to pull out, you actually have the alarm that come out. If you don't have electrical system, then you will not do the alarm, right? So you may have some of the battery backup, they to be there to cause the alarm. Of course, if you have a device that's very far away, then have no human being, even you have an alarm, is useless. So some of these device, a lot of things need to be thought ahead of time. But then where you're going to place the alarm, how you're going to place the alarm in terms of the device wise. So in terms of physical device security, right? Another part that is important, in order for them, let's say it's a remote site, then you need to have logs of all these, some of these equipments digitally sent to somewhere, right? If certain things happen already, it may no need just to have a alarm. It may just, the alarm may be just triggered by sending some SMS to some of the administrator that is somewhere or nowhere, and then you may trigger some of the CCTV to look at the thing, and then trigger some of the door to lock out, so that the person who trying to do something funny and may will not be able to run away from that. Okay, so physical defense is very important. Okay, the other portion is on hardware vulnerability. Okay, I will not say very common, but then there is possible to do hardware vulnerability. Then how to get in access to the firmware, okay, and SD card. So you just need to solder some of the SD card into the system itself, and then it's possible to hack some of the physical system. So some people may access the UART. One of the very famous case is the router. At the router level, it is possible to plug into the UART and then hack through the thing, right? That is a lot more serious than just the doorbell itself, because it is the firewall, it is the defense equipment. So network equipment is a lot more important than some of the non-network equipment, right? Okay. So hardware vulnerability, some are more important than the rest. Just as I mentioned, network device is face the most attack in terms of hardware vulnerability, right? The next thing that we talk about, important thing is obviously it is about medical devices, because it can kill someone. Okay, because if it's not well protected, it may get someone killed, right? Of course, voice over IP hardware is the same as a network device, so they are the same class. Okay, some of a lot of other equipment is just an endpoint device. They are not as critical. But then storage is a very important equipment. So NAS device is the same class as it's a network device. So I classify them as a network device, right? They belongs to the either the server or belongs to the network class. They are a lot more important. Some of these other equipment that is like what multimeter, media player, music player, camera, automation, real player, television, they are real endpoint device. They have less importance in comparison to what I just mentioned. That few equipment that is a lot more important. Okay, this 4 equipment is a lot more important. Of course, medical device, even though it's endpoint, but it will kill someone, so they are important. Okay, because it is not possible to protect all sometimes. So you look at the importance and you protect the most important one first, right? And you rather pay a little bit more money for those important one. Okay. Do we have camera here? Talk about camera. This one may be a CCTV, so I may erase this thing. This may be because if your CCTV is down, then you're gone again. Game over, right? So they are important. This is important as a network. Okay, 5. Yeah. So the firmware vulnerability. So all these equipment require a piece of software to run. That may be a web page like this. Okay, this is like a white page. A lot of them doesn't come with a web page lah, by the way. Okay, so they are embedded system. Okay, they may not have operating system at all. I mentioned already. If you talk about ARM, Mbed, and then Arduino, they just libraries. Okay, so that used for control of some of these IoT equipments. Okay, and they just send information out. Okay, so some of these firmware can contain security vulnerability, and after this after they release the vulnerability, and then is it possible to patch? Not all IoT equipment are patchable. Okay, the keyword here is not all firmware are patchable. It depends on the design of the firmware itself. Okay, so there's a key importance. Okay, I mean, if you look at like a PC, of course, but then if it's not a PC based, if it's a much lower end one, they may not be patchable at all. Okay. So some of the vulnerability, because this is looking from OWASP top 10. Okay, so some of them is like if you have a camera, then the default login, then you should not have a default login. Yes, that's very good, right? Distributed denial of services, if the thing is it's a much lower end system, and then it's like a camera system, right? Then it may be infected with hardware is still connected to the network, and then one day someone can write some program and hack them and send it out of the thing. So there may be some vulnerability that is denial of service attack, right? This is distributed, so there's a lot of them. So this one is mainly talk about the camera systems. Okay, the default password was not changed. The default password for if you buy a Hikvision or Dahua, okay, camera, Chinese camera, these are two very common camera. Their default password used to be 1 2 3 4 5, which is damn simple, and people don't bother to change the password. And that's where this thing is, first of all, the default credential, and then followed by the denial of service attack. Okay, this was happened. And the next thing is this camera, if it's not even password, it's not done out, the people may just go in and then look at the camera, right? Reputation and whatever has been spoiled because of that. Okay, so there's some of the key things when we talk about some of this firmware vulnerability that, well, Cisco written here known. Of course, there are much more than these. These are just some of the sample. Okay, these are just some of the common sample. It is a lot more than this. This is just scratching the surface. Okay, then the other part is out of date firmware. Is the some of these things out of date or is still within the date itself, right? So there are a lot of IoT equipment that may not give the latest up-to-date operating system because the manufacturer, end of the day, when they manufacture, they may be thinking of whatever they build, and then so long they can sell it, that's it, good enough, right? Some of these things is written in some of the older operating systems. Think about this. How often do you look at your own laptop BIOS? Do you do update on them? It's not just the vendor itself. They have updates. But end user like you and me, do we go in and do update on our BIOS? I'm not talking about the operating system. I'm talking about the BIOS itself. Okay, so there's one big thing that a lot of time end user don't do it. Whereas for your phone wise, there's once in a while there's a patch. How often do you update your phone, your mobile phone? Right, the OS, right, and then are they updates for your application? Worse, at least for your mobile phone, it comes with a package manager, so end of the day you know how you still can press here. Your laptop, you probably will purchase certain licenses that only give you some older version of the software, the application, right? And every time you want to do it, you may have to pay. It means that as the end user want to do that. I'm talking about just IoT equipment itself, right? So these are some of the issues. Next thing on top of that, not just the firmware, how about your antivirus? Okay, and how about your firewall? Okay, your firewall may comes with what you call it, the intrusion prevention system that has some signature, intrusion detection system that has some signature. Do you update these two at the network level? This is at the host level. Okay, so these are some of the questions when we talk about firmware vulnerability wise and in terms of the update wise. Next, buffer overflow attack is some of the vulnerability, as I mentioned, right? The program, some of the software, the programmer did not do proper data check. So if there are overflow of data, the whole thing may crash. End of the day, because the memory is too full out, the CPU read the wrong memory and it doesn't know what to do. That's the whole machine hanged, and it doesn't know what to do. Then it does a reboot, and because it keep on like that, the machine just keep on hanging. It doesn't know what to do, right? Until you refresh and whatever. Okay, so these are some of the things possible. Corrupted data, denial of services, too much of the information goes in, and allow malicious code to run into a target system. Okay, the other part is on backdoor installation, right? Some of the attacker, when they sell you the thing, they really create the backdoor, and at the end of the day, they can run the backdoor and run some of the malicious code and control the system itself. Okay, some of these things are basically a network diagnostic and testing tool that is left behind and did not properly switch off or remove, and cause the unauthorized entry. That's where the backdoor comes in. Okay. Firmware update issue, right? Some of this IoT security has never keep up with the growth rate of the IoT device. Okay. Not all the hardware manufacturers are able to look at the device and provide a security vulnerability patch. Okay, the patch does not exist. Okay, sometimes it does not exist at all, right? Some of the device may not be patchable, okay, updatable or patchable, as I mentioned, right? IoT in organization may have a number of in terms of thousands or tens of thousands of the devices, sometimes even millions of these devices end of the day. Okay, it is itself to update and patch. It is a challenge by itself. Think about Singtel StarHub M1. Right? Because they have many mobile phones with them. So installing and update the patches is tough, right? Even for notebook, we have thousands of them. So to do update and patches is not so trivial end of the day. Okay, it is important to verify all the upgrades and patch comes from a proper source. Okay, because there are many cases that end of the day, the administrator just download whatever driver over the internet without checking, and end of the day, and that thing becomes a bad software, a bad malware, and then cause the whole entire organization to go down. Okay, so there are many cases that's like that. So as a proper administrator, need to check whether the source is correct, and even the source is correct, right? Because recently there was a case called the SolarWind case, which is a company. The source was correct, but then the thing is, the source was being modified by some hackers. So it's not only need to be verified, it need to be signed, digitally signed, and make sure that the person who compiled it, you get the digital sign, the binary version, and not the source code version. So yeah, so that's where the thing comes in. The firmware update signed and verified. Okay, you need to be using a cryptographic sign and double check with the company, is this the correct version, right? So they'll provide you whether you've either MD5 or SHA-1 hash that allows you to do the necessary check. Okay, then update solution, right? It is necessary to keep a database. It's easy to say than doing. Okay, it is actually very difficult to do that. The thing is, keep a database is okay, but keep up to date a database is tough. Okay, you can go and do asset management and figure out what are the assets available. You do one time, but the second round, a few minutes later or a few days later, you have a new asset. You may not know, right? So then it is a huge coordination job between people. The easiest way to do that end of the day is at the network level. At the network level, okay, the network need to be smart enough to be able to do this. Okay, that piece of software is known as IPAM. Okay, so IPAM allows you to, it is IP access management. So basically, it helps to keep the database of equipments, because this thing make use of your IP address. Okay, that will lower the pain part on the update portion, because it is actually humanly not possible to keep on looking at whatever you have inside a network. The key part is your network. Okay, so the other thing is the firmware need to be updated, right? Actually, in actual fact, need to be verified, signed. Okay, another keyword is tested. Okay, so you need to have an environment to test your firmware before you actually update them. In 99.99% of the organization, most organization doesn't have this because it's expensive. Okay, but by right, okay, to do a proper cybersecurity job, by right, I'm talking about by right, a proper cybersecurity job, it should be tested before you do an implementation. Okay, some of the way to do it is, example, you can have a sandbox to test it out. A sandbox, what I mean is basically a virtual machine to test it out before you actually do the implementation. Right? You don't want to just throw in inside there and then crash the whole entire thing. This happened many times already, especially we talk about Microsoft Windows since the day, if you know about when we have internet connection, and then we have the XP day, the Windows 7 day, and Windows 10 day. Okay, even today, okay, Windows 11. Once in a while, if the patch or whatever is not stable, it crashes the whole entire operating system, and you can no longer boot it out. So, as big as Microsoft, a company, it is still a nightmare. Okay, basically, the most important thing is you have a test environment and test it out before you actually do the implementation itself. Okay, which is critical, because you cannot trust anyone. even the vendor, even as big as Microsoft, okay, which is a multi-billion dollars company, is not trustable because simply because things will go wrong because of the hardware that you have end of the day. Okay, then you need to have a plan, okay, to go and check the manufacturer website for any other updates or not, right? This whatever I'm saying in the first part is you should not need to go and do this manually because you will every day do unnecessary updates. Okay, then you need to have it's important to subscribe some of the security vulnerability services. Okay, if you want to do a proper job, right, such as US cert, or Singapore do have some of this Singapore cert also, right, to look at some of this IoT equipment and everything. Okay, as mentioned here, best is to have an automated system. I mentioned IPAM, which is expensive. By the way, Cisco system does not work with Microsoft. Okay, Microsoft comes with a free IPAM, free. Okay, but it doesn't work with Cisco. So end of the day, if you're running a Cisco system which is nice, Microsoft system which is because as part of your network, your Active Directory come from Microsoft. Okay, for most businesses, the IPM portion, unfortunately, you have to pay extra just to fit these two entire systems together as a single system. Okay, so that is a very important part that most people need to start understanding. There's a thing called IPAM. Okay, that you need to pay, and it's not free because Cisco system doesn't work with Microsoft at all. It doesn't work that way. Okay, and then it is important any firmware update and patches are digitally signed, as I mentioned. Even more important, tested before installing. Okay, this is the missing word over here. The notes. Okay, so even if this notes is not enough, it is important to test. Okay, next thing, routing or operating system. Okay, it is possible to root an operating system. Basically, we mentioned just now. Okay, you may go to the BIOS and whatever to go and do these things, right? Basically your boot and your debug mode, right? This is basically what this thing is, right? And then you root it is basically going into here. That's all, right? So it's not good to root any operating system. Most of the system should not provide root access by default. Okay, you should have not a direct root, only until it is necessary. Then you provide a root access. Okay, it should not be a default one. It should need to gain entry as a power user first, and somewhere to the power user, then you can go into your root mode. Okay, so it should not be providing root mode straight off. Okay, next. Okay, then we go into the other part, threat and mitigation of physical devices. Okay, some of the threat and mitigation, some of the possible way is, first of all, you need to have username and password. Basically, is direct access control, the common one. Then it's even better if you have role, you have an Active Directory and whatever not. At the end of the day, it's possible to have a role-based access control, basically security groups. Okay. Let me write it properly. Just give me a minute. The pen doesn't work very nice here. Let me just try to write it nicely again. Security groups. Don't know why is it so not nice to write here. Let me write at different places. Okay. Draw it up here, and then I think it's better to write it like that. Yeah. Okay, security group, GROUP. Okay, security groups. Okay, so there's role-based access control. Okay, that's known as role-based because you have a security group. You group based on people, based on their individual roles as responsibility. Where's the mouse goes to? Responsibility. Okay, the next level is mandate access control. So this is level 1, this is level 2, then mandate access control. Okay, for more critical system, you not only have role-based, you have security level, assigned security level such as a Cisco router to provide users based on their security level clearance. So it's a more hardened systems. So they have, let's say you have administrator, right? In non-discretionary, you have simply a thing called administrator. But in mandate access control, administrator will break into several parts. So depends on the security clearance of the administrator. Oh, are you able to reboot the machine? Oh, you are be able to do more. You can connect to network and can ping to network. Or oh, you can do even more. You can do change configuration of the network equipment. So these are known as mandate access control. Sometimes we call this capability. Okay, that's a keyword lah. If you look at the actual operating system that support this thing is known as capability. So they have multiple levels. Okay, in Cisco there are 15 levels. Okay, Cisco router. Okay, next. On top of it, if you still want to have on top of it, so all these are attribute on top, whatever it is. Okay, then we may want to have, okay, I want to log in, but then I want to have, let's say, a third-party login and multi-factor authentication. I want to have a one-time password, right? So this is number 4. So let's say you want to have a one-time password. One-time password, right? So that allows you to be able to factor in terms of how the user has been accessed at what time and one-time password. At that point in time, is the person within the same geographical region with the same geographical region? For example, you're in Singapore, you log in to Singapore, the server is in Singapore because the time is the same, it's synchronized, so you can log in. Okay, so that's the attribute, right? So at time of the day, because you're at exactly the same time, same region of the time, so you can log in. If you're at a different region of the time, you cannot log in. That's number 1 that can be done at that level. Second thing is your IP address. It may be the same zone, right? But then, example, Singapore and China are within the same time zone. But if you're in Singapore, can you log into a Chinese system or can the Chinese log into a Singapore system? Based on the IP address, you can do the blockage at that level because they are given a different IP address range. Okay, through that is where the attribute-based access control allows you to go further in terms of final way of tuning the access control. Okay, so that helps in terms of the control for the IoT. So now the whole entire world can configure and log into your IoT equipment because they are from another country. Why do you need to have someone from another country to be able to log into your IoT equipment unless you specify so, right? Okay, let's say you have you are an administrator for ASEAN, so several countries. So they may lock down a physical set of IP address. This is the only IP address that can control. Let's say you have a Philippines, you have Indonesia, you have a Malaysia. So that particular station only one and only one station for the particular IP address. The rest are all filtered out. Okay, so that is also another way of looking at it from the attribute access control. Okay, next thing is there's a thing called access control concept. Some of the modern access control asset, which is known as OAuth. OAuth actually is not a very secure way of doing it because if you start asking the people in IETF, basically the people who specify this thing, okay, there are a lot of issue with IETF, with OAuth actually. Okay, in terms of that, because it's a combination of a lot of things. So exactly what is OAuth? OAuth example, the very common one is, let's say you have a Google account, and I can make use of a Google account. Okay, this is the authentication server. Let's say this is Google. and I want to access this particular resource, right? I want to log into here, so I will check with the resource owner and then come back to Google and Google for authentication and then get access to this particular server. This is not a very good way for IoT equipment. It is not a highly not recommended way of doing any IoT authentication at all. It is a very bad way of doing authentication. Okay, IoT, if you want to have, why people want to do this? Because they want to have a single sign-on UI. But then IoT equipment is not a UI device. You don't need to have a single sign-on end of the day. Okay, so do not, if best, do not use a single sign-on or a ITF, OAuth way of doing authentication. It is a very bad way of doing it. One of the things that a lot of people are using in Singapore for this perspective is SingPass. Okay, so actually I don't, the way I do it is for the convenience, but then hope that they are do enough cybersecurity for this SingPass system. Okay, it is a kind of OAuth system end of the day. Okay, this is just a process that talk about OAuth. Identity management. Okay, the key part is identity management. There are many devices that can be managing through their access of data, right? They communicate with one another. It is not uncommon, so it's very common. Like a double negative word, it's very common for sensitive information to be transmitted over this way. Okay, so identity management should be handled, okay, access for other information, other resources. Okay, the proper way is the identity management should have a different pathway for whatever it is. Basically, you're talking about the username and password of these things. Okay, so you need to do a proper username and password for whatever IoT equipment that you're going to have. Okay, you may have a lot of the IoT equipment, may have a lot of them end of the day. So you want to have a proper way to be able to log in and then be able to update and do whatever things. It need to be properly designed in a way that it need to be secured and to be accessed. Okay, so the access control is very important, right? It is not a good method to go through OAuth, as I mentioned, but if there's a possible way, normally some of these equipment come with a thing called controller, right? If you look at how wireless do it, right, they have a thing called architecture, then they have a thing called master controller that has a piece of software that connects to the master controller and that control most of the controller. Okay, so let's draw the word, write the word properly. Okay, so they have a piece of software that allows you to connect to a master controller that control many controllers that actually and already connect to all the devices. Okay, so this is a proper way of doing a processing, and the identity management system need to incorporate such a system inside there. So at the end of the day, you would have a proper way of doing management at the end of the day. No matter how much it grows, because whatever device at the end of the day that you have should come with a proper controller and should be controlled via a master controller end of the day. Okay, not a lot of IoT equipment is designed in such a manner. Okay, this is not a cheap process. This is a very expensive process. But from a cyber security perspective, it need to be done in this particular way. So the end of the day is a much easier, much manageable system end of the day. Even from identity management perspective, even from asset management perspective end of the day. Okay? So it comes back to confidentiality again. IoT, it is very important. We talk about CIA, confidentiality, integrity, availability. So it is important to run encryption for whatever mechanism it is. It is it makes things easier. Things are not easily hackable from that way. Password should always be encrypted. and plus sorted. Okay, all passwords should be different. Okay, encryption of IoT data is critical. Okay, should not contain any if there is a critical information that's sent. IoT equipment are vulnerable because some of them are older, right? So password should have the sort mechanism inside there. So some of the modern one types comes with this. The best is you have an active directory at the back to keep the security group at least minimum to have that level. Okay, so at the end of the day you have a proper password management system if you have an AD. I'm not saying that AD is 100% secure. Okay, there are weaknesses inside AD. Microsoft is still trying to solve this issue over there. Okay, but it's better than nothing, right? At least it's SHA-256 today, which is better than a lot of systems that is your SHA-1 and MD5 for your hash within your password itself, and worse, it is not sorted, right? There are a lot of systems that is worse, right? AD at least provide hashing and sort, okay? At least that two minimum, and plus updated hash, okay? So at least these three things is the bare minimum that you're going to have for any IoT equipment. But then unfortunately a lot of IoT equipment, when they're connected, they are not using the enterprise grade for security for Wi-Fi if they're using Wi-Fi, right? So it's best if all the IoT equipment is going through at least the enterprise grade authentication method, which is the proper 802.11i method for authentication. A lot of them is not WPA2 method. A lot of them are still pairwise key. Okay, not your enterprise grade WPA. Okay, so best is to do this enterprise grade. Better do a proper written word again here. I think because of the way the pen is been designed, enterprise. Okay, great. Okay, not PSK. A lot of systems are still PSK. Okay, you still come back to vendor lah, end of the day. So encryption at constraint device, a lot of device doesn't have the processing power for some more robust stuff. The reason is AES require 240 megahertz and above. It is possible today. Okay, a lot of time people say it's not possible. The reason is we are talking about pre-2015 system. By the notes, by the way, this notes is 2016. So Cisco actually not really up to date in that particular understanding. Reason is because by 2015, right, there are a lot of processors, example STM32, have become a lot more affordable. ESP32 has become a lot more affordable. The first generation of ESP32 has already existed in 2015 by then. Okay, so in 2015, it is, I mean, at least the STM32 is there already, right? ESP32, I need to double check. I'll get back to you on this one. But anyway, at least some of these things can easily do 240 megahertz. In actual fact, your 8266, ESP8266, even though in 2015 is really a 32-bit processor, it's also a 32-bit processor. So it can be done. Okay, AES can be done because all of them are at least 240 megahertz, unless you use something that is not 240 megahertz and above, right? So that's one thing, and they are not and they can be in low power mode. So engineers need to be trained. A lot of these things already can be in low power mode. Okay, to consume less power. You don't need to resort back to things like STM8, which is 8-bit only. Okay, because STM is one of the company that actually a lot of people are using, or the other one is Texas Instrument, your 430 low power system. Yeah, try to avoid some of these systems nowadays, right? Because they are not powerful enough. The application to write them is very complicated. There's no point of going to these things anymore, even though yeah, they're very cheap, but at the end of the day, you're sacrificing the security portion of it, right? So most of the vendors should move into some of these better performance CPU, which is equally cheap, and at the end of the day but give you a lot more better performance, and at the end of the day low power efficiency at the same time, and at the end of the day a lot more ability at the end of the day. So at that point in time when they written there's no standard, okay, but then the standard now is already come out. The standard for lightweight cryptography, the standard is known as SCON. Okay, so there are proper standard to do this. Of course, SCON can run in 8-bit mode, but then the best is SCON to run it on 32-bit CPU. Okay, it is about 3 times more efficient in comparison to AES. Okay, simply in terms of the running, it doesn't need to have special hardware like AES, because some of these things like 430 require to have special hardware if you want to start running. If you want to start doing AES and you want to start doing elliptical curve, okay. So that's one of the key portion. SCON by itself is very good because it is a better authenticated crypto in comparison to AES at a symmetric level. And then you can obviously you want to do elliptical curve, you can do it at ESP or STM32 easily, right, with the Sodium library. So next thing is symmetric key. Just now we talked about symmetric key. So AES is one of the very famous symmetric key, right? It is a block cipher. Okay. And what does it mean by block cipher? So every 32 bytes, we do one encryption. So every 32 byte we do encryption, at 32 byte do encryption. Okay. So it is it is because it's a very efficient system, so it's highly usable, right? There was a point in time that people using public key cryptography. Yes, in early days in 1976, right? PC was using it, but then it was very, very slow, so not a lot of PC are using that. PKI is for the recent years because of, just imagine, in the mid of late 90s and late 80s and the early 90s, we have a 32-bit system, 386 and above, right, and 486 then. So and plus the connectivity of the internet. The internet comes in much further down the road. Well, after 1995, when almost everybody has a 486 and above. So all these things is using very powerful 32-bit system or even 64-bit systems at that point in time. So there's no issue of running a proper public key from cryptography with 240 megahertz and above, right? Whereas a lot of low powered system early days, during then it's not possible. So public key is good, okay, provided you have a very powerful computer, not necessarily embedded, okay. Most of the embedded system is a lot more efficient to run a crypto, symmetric crypto. The design mainly is you use what you call it, the which is further down the road. Okay, not here. You use what we call it, the key exchange, which we will cover again, okay, for symmetrical cryptography. End of the day, one of the famous one is elliptical curve, okay, ECC. Of course, before ECC, Diffie-Hellman, okay. Diffie-Hellman is more the early days in terms of the key exchange. Of course, modern days we are looking into ECC or ECDH. Electrical defi human. Basically, it's still defi human. Okay? In terms of the part for the cryptography itself. So this is a design of a certificate. Why is still important to talk about certificate? Because your IoT equipment may not only just reside on the endpoint device, it may be all your networks and your servers and what so not, right? So some of this PKI is important for some of these routers and switches and so on and so forth. So these routers and switches and what so not can run, because they are a lot bigger, they have a power, so they can run PKI and certificates. Okay, mainly certificate follow a particular standard known as X.509. Do note about this X, right? I cover this X in the earlier lecture, last week lecture. So X, okay, if you remember, your so-called OSI 7 layers is X.200, just to refresh with you, okay, and it is based on X.900 OTP design for layers. So X.500 was the original. It's called known as directory services. Okay, this was never fully implemented worldwide. It was later stripped down and becomes a small portion of it, which is what we call in IETF. This thing has been stripped down, which is known as LDAP, which is directories that come with username, password, and certificate. So you have a directory that comes with username, okay, password, and certificate. And the certificate portion actually is this 509. And then what is the process? You have a PKI, you have a certificate authority. Okay, so this is a CA, certificate authority, and it issue certificate to individual. Okay, so that's the main part of it. Okay, so stored by the CA, right? Okay, and then someone want to verify this certificate. They goes to they first of all, this is get the issue of the certificate, and there is an exchange of the certificate between public Alice and Bob. So you have a cert. Okay, it can be a server cert to verify the server whether it's real or not real, and then you take this, the client take the server cert and send it to the CA, the certificate authority, and check whether it's okay or not okay. Okay, the design is actually in the real world is not exactly like that. Well, if you want to have a certificate database and certificate authority, it should not look 100% like that. This part is your Active Directory. If you think about it, okay, Active Directory is nothing but a Microsoft implementation of LDAP. Okay, so repeat again. We have X.500 that was never been implemented. IETF take X.500, which is IETF, basically Michigan University, took X.500 and designed a stripped down version of X.500. They kept the certificate format, okay, and Microsoft designed a variant version of LDAP, which is we know today known as Active Directory. Okay, at the end of the day, it is a certificate database, as I mentioned over here. See, your username, password, certificate are all stored inside this database itself, and your certificate authority will go there and pull out the certificate for the final verification. Okay, and that's all for this particular chapter 3. Thank you very much. I will see you next time. Bye bye.